Hello, everybody, and welcome to episode 159 of I Wish You Were Dead, a podcast about things that used to be alive. My name is Mike, that is Gavin, and that is Fia. And friends, have you ever been doing something but really been actually paying attention to something else more?
Yeah.
That's about 80% of my entire life.
Yeah.
So that's what I'm doing tonight during the podcast.
Oh no!
Is there a Mets game?
Not only is there a Mets game on, you're 100% right about that, but the Mets are playing the Pirates.
Oh.
And there is only one player on the Pirates. I know. Pirates, not a good baseball team. There is only one player on the Pirates that is worth watching.
Okay.
His name is Paul Skeens. He's a very good pitcher. He he put the first two guys on just as a challenge for him. And then he got one of the Mets batters to ground into a double play and then got the third out.
Sure.
I'm a Mets fan. I would have rather the Mets scored. But I can appreciate the game there. I can appreciate the fact that he's just good at his job.
Yeah.
And it'll be a fun thing to watch. So, I'm here. I'm recording the podcast. We're gonna have a good time. But I'm not 100% here.
So, are you 80% watching the game or on the pod?
We're on a commercial. We're on a commercial right now. So, we're good. And now they just started the next half inning. The Mets are pitching. And, David Peterson's pitching. I like David Peterson. He seems like a nice guy. Seen him before. Don't need to see him again. At this point, I'm 90% on the pot.
Okay, cool.
Okay.
But when the Mets are up, and I get to see Mets offense against one of the best young pitchers in the league, I might miss a couple thgive
Yeah.
All right, well, you heard that,
know.
listeners. So please feel free to roast Mike in the comments. Give us that sweet online engagement.
Speaking of engagement, someone's engagement is ending pretty soon.
In a good way.
Yeah, I'm getting married on Friday.
Woo.
Hey, Pia!
All right, well, with that, we can start off this episode. It's going to be an interesting topic. Probably one of the more conceptual topics that we have, especially in the recent run of episodes that we've been doing about taphonomy. That sounds like a funny word, very similar to another word that we use a lot in paleontology. But before we get into the episode, Fia, do you want to do some housekeeping while Mike looks up at Today in History?
Okay, first off, I looked it up in 30 seconds ago, and I've already got one. I've got two, actually.
Y'all, we're doing a little Uno reverse today because
Ooh.
I don't have a Seagrass corner.
Okay.
Don't worry.
That's okay.
Don't worry.
It's fieldwork season. We get it.
Yeah.
It's fieldwork season, and also, this podcast can't be too terribly long, so we're going to keep it nice and tight here.
Don't forget to rate the show on whatever platform you listen to us on, and to follow us on Twitter, Facebook, and YouTube to give us feedback about the show and any future topics you would like to hear on the pod. And if you would like to be guests on the show, be sure to fill out the guest form. All that stuff can be found in the show notes. Kevin, what is next episode topic?
I don't really know, because next episode is an episode that ends in 0, which means it's a Mike Takes the Wheel episode. Mike Takes the Wheel, volume 16. And for the first time of those 16 episodes, Mike has said he already knows what we're talking about.
You're damn right.
Are you going to tell us, or are you going to save it?
I'll give you a little hint.
Okay.
I was perusing the Wikipedia pages of various politicians from Alaska, and I found a series of coincidences that will be discussed.
Fascinating. There are 2 of them that I know of.
Is Sarah Palin going to be involved in this?
We're going to find out.
That is one of the 2 that I'm aware of.
Okay.
Anyway, interesting. Alaska's an interesting place for a lot of reasons. But yeah, that'll be interesting. I'm looking forward to that.
Have you ever been there?
I have not.
You seem like an Alaska kind of guy.
I did once apply for a job there. I didn't get it. But yeah, it seems like an interesting place. I know a handful of people who live there for quite a while, but never been there myself.
I think you'd be good over there. All right, Today in History?
Yeah.
All right, so May 14th, 1787, delegates gather in Philadelphia to draw up, what are they drawing up in 1787?
Constitution?
The Constitution of the United States. So today in 1787 is when they gathered together to write the Constitution. Also in 1796, an English doctor administered a smallpox vaccine. Today in 1804, Lewis and Clark set out on their famous thing. A patent for condensed milk happened. Bunch of cool stuff took place today in history.
Nice.
And that's all I got. On with the episode.
Yeah. A quick little administration science update. I missed this last episode, so I have two just real quick things for today. Firstly, the Trump administration has basically cut the research and development wing of the Environmental Protection Agency to zero, and laid off.
That's a good thing, right?
Oh yeah, definitely a good thing. Laid off a lot of the researchers there, and basically environmental research is just kind of stopping. And it's not like it's just climate change stuff. Most of the research that the EPA does is into things like water quality, air quality, industrial waste, and contamination. So, if you love being able to pollute the environment with no recourse at all, great past couple weeks for you. There'll be a link to a news article to that in the show notes. And then the other one is the National Oceanic and Atmospheric Agency, or NOAA, basically ended funding for maintaining our data collection equipment on that we use to, look at the amount of sea ice, snow, and glaciers in the Arctic. This equipment is still going to be remotely collecting data, but they won't be maintained anymore. So if something breaks, and it's the Arctic, so it's gonna break, that's just kind of the end. And these data obviously are, important for monitoring the effects of climate change, but also they provide a lot of, really vital data for weather forecasters, fishermen, and ships, like cargo ships that navigate the Arctic. That's just going to be gone. And all that is on top of NOAA cutting a very large portion of its staff to begin with. So there'll be a separate news article link to that in the show notes below. But anyway, here today we are talking about taphonomy, which
Not taxonomy.
Not taxonomy, very notably. Taphonomy, Taphonomy. It is a weird bit of paleontology. Firstly, because of how similar it sounds to taxonomy, because taxonomy is a much more commonly used word.
Yeah.
Taxonomy, the more common word, is how we give scientific names to organisms and how we group them together. Taxonomy is, why we are Homo sapiens, and how we know our next living relative is chimpanzees, the genus Pan. Taphonomy, and for the rest of the episode, I will not use the taxonomy just for, sake of simplicity. That word is going to be the one we're talking about for the rest of the episode. Taphonomy is the study of organisms, like how they decay and how they become fossilized. So it has been described to me as the complete series of events that leads from a fossil being found by researchers or anybody else who finds it.
So it's basically how to become a fossil.
More or less.
Sweet.
And this is often just sort of phrased as how fossilization happens, but there's a little bit more to it than that. And it's also a fun activity to do with kids. There's a interesting little demo. So, any science teachers out there, here's something free. So first, you'd have the kiddos pick an animal. All of this that I'm going to say applies to plants too, but we'll talk about that later. For simplicity, just go with animals. So, Mike and Fia pick an animal.
A goat.
Okay.
I'm going to go ahead and make Mark upset.
Pandas?
Panda.
Yeah. All right, a goat and a panda. And so you'd have, your kids all just in their minds think of an animal. Then you'd pick a couple, probably the more animated kids, and tell them to act like said animal. Let them crawl around. And obviously this is for some younger kids. Please don't ask 15-year-olds to crawl around and act like a goat.
Gavin, I don't know if you remember how we all met, but it's not too terribly far off.
Yeah, fair. But yeah, and let them go for a couple minutes, or a couple seconds. Obviously, like I said, this works better with younger kids, and so then you ask them, what is the first step in becoming a fossil? Mike and Fia.
Dying.
Did
I get it right?
Absolutely.
Suck it, Fia. Yes!
Well, Fia said it too.
Yeah, we said that at the same time.
Oh, did you really?
Yeah.
Sorry.
Thea, you don't have to suck it anymore.
Okay.
Almost certainly, because they're children who might not have like the firmest grasp on death yet, they probably won't say that. And so you let them guess a couple wrong answers, and then you tell them the real answer, dying. At which point, you tell the kids, all right, go ahead, die. And several of them will probably keel over and act like a dead panda or goat. That's just a fun way to get kids out of the seat. And
Classroom management right there.
Absolutely. And so this next part, this can be where the demonstration kind of ends, since the next parts aren't as fun to play pretend with. All right, so now, sadly, we have a dead animal. What happens next? Mike and Fia.
A funeral?
Okay. It's sort of.
I'm gonna go with their gut bacteria and probably other stuff on the outside too begins eating at the fleshy parts of their body.
Okay. You're not wrong, but it's not what I'm looking for. I'm looking for specifically like in the steps to becoming a fossil.
I assumed that was part of it because you got to get rid of all the other crap.
I feel like first you gotta get buried.
Bingo.
Really?
Yes.
Okay.
And so that is by far the most important. Well, I guess dying probably is the most important. Although you can bury things while they're alive. So no, probably burial is the most important. This is one of the main things that makes becoming a fossil so rare. So like fossils themselves are not particularly rare, but that's because of how many individual organisms are living on the planet at any given time. But the odds of like any individual organism becoming a fossil and lasting long enough for somebody to find it are extremely rare.
Mm-hmm.
But just, over millions of years and like over the course of Earth history, like quadrillions of individual organisms at the very least. Just like, law of large numbers, it's going to happen enough times to be relatively common. But we'll talk about ways that that's a little tricky. So, yeah, the first step is becoming buried. Again, sometimes that can happen while you are alive. Sometimes if the burial is what kills you, that is like primo fossil making potential. But yeah, so say you're an animal that lives in like a very sandy desert where you might get covered in sand, like even while you're alive. If you just like sat, eventually you would get buried, just from like wind blowing and stuff like that. Getting buried is fairly easy. If you live in a forest where there's almost no sediment being deposited for you to be buried under, becoming a fossil is quite hard. For example, we have absolutely zero, unless this has changed somewhat recently, tree sloth fossils.
Because they were in a forest?
We just don't have them because they live in trees, in forests.
Trees are notoriously above the ground.
Yes. And not only that, but, if you think of a forest, unless there's some kind of weird Dust Bowl situation from the 1930s, it's not like a bunch of sediment is going to get brought into the forest to bury something that dies. Or a big flood or something like that. We have lots of fossils of their cousins, the ground sloths, because they ventured out and didn't just live in forests. They lived in plains, and some of them even were like quite aquatic. I don't think we've actually done a sloths episode. We'll do that at some point. But yeah, as it turns out, living solely in trees in forests is a pretty decent way to dodge the fossil record. Like I said, sometimes there are specific events that happen that cause burial in places where it might be rare, such as floods or volcanic eruptions that, spew out a bunch of ash, and those tend to make terrific fossils. But those events happen so infrequently that we don't consider them like the usual,
Yeah.
And the main reason, on top of just there's no sediment to bury you to begin with in places like forests, there's the whole concept of scavengers to consider. And in that is sort of where those gut bacteria that you were talking about come in, Mike. And
Perfect.
So, yeah,
Gavin,
lots
I
of
have a
species.
question.
Yeah, go ahead.
How long does it take to become a fossil?
That is a question.
Do we
Um,
know?
The answer that will come up when you Google that is give or take 10,000 years.
Okay.
The real answer is it depends a lot on what exactly you mean by a fossil and the depositional environment that you found the thing in. So we'll talk about it a little bit in a second, but if you find, hypothetically, if a bone sat on the surface of a forest and for one reason or another was kept in a box, so no scavengers ate it, no bacteria broke it down or anything, and just sat in a box for 10,000 years, I wouldn't really call that a fossil because it's not altered in any way.
Yeah.
And we'll talk about the different ways that they can be altered here in a little bit.
Okay. So, loaded question.
Very loaded question. Not quite as loaded as what is a species. But yeah, the simple answer is roughly 10,000 years.
Okay, cool. Thank you.
Yeah. But yeah, back to scavengers. So lots of species, particularly invertebrates and microbes, make it their full-time job to eat dead stuff. Things like maggots, beetles, worms, and stuff like that, etc. But obviously many vertebrates, coyotes, vultures, hawks, crows, things like that, they will scavenge, even if it's not their only source of food, but it is something that they will regularly do. And so with those invertebrates, mostly, a lot of insects and fungus and bacteria, this typically results in the bones just becoming disarticulated. So like being pulled apart so they aren't like connected to each other anymore, but not like dragged apart. If you've ever watched like a time-lapse video of what happens to roadkill, how first it kind of bloats and then all the flesh just kind of disintegrates and sort of the bones just sort of spread out a little bit.
Mm-hmm.
Whereas with vertebrates, sometimes, they'll just rip a leg off and take it away so they can eat it in peace.
Yeah.
And so, even if, a flood or a sandstorm came through and buried the animal right after that, that fossil, it will now just be missing a leg. So those are the kinds of things you have to consider with scavengers, is that pretty quickly, especially the ones that are like really dedicated, that is their entire lifestyle scavengers, they will be on that body almost immediately. And so if it doesn't get buried very quickly, the odds of it becoming a fossil, like already being super low, just like fall off a cliff. And so after that, depending on how long and how deeply the body is buried, so once it gets buried, different things can happen. And we generally refer to these things as diagenesis. So like things that alter it in some way.
Okay.
The most common one that you'll see with fossils, especially vertebrate fossils, is called mineralization or permineralization. Mm-hmm. And so fossils over time will absorb different minerals that are, either in just like the rocks surrounding them or in the water surrounding them, especially if they're like terrestrial fossils with groundwater. Mm-hmm. And so especially if they're in a, pretty sandy type of soil, there's a lot of groundwater flowing through it that has dissolved minerals, and just over time, as the water flows over that, it will dissolve a little bit of the bone. It doesn't even need to be like acidic, just because, osmosis or diffusion, because there's,
Yeah.
less of that mineral that bones are made out of in the
Mhm.
water. It will just passively dissolve a little bit of it and
Okay.
deposit whatever the main mineral in that water is. Often that is some form of quartz or some form of calcite. Those are sort of the two main ones. But it can be other things like pyrite that can happen occasionally. And so this is why often when people, and actually just had somebody do this the other day, somebody that I knew from high school messaged me on Facebook and was like, hey, can I send you a couple pictures of this bone I found, and can you tell me if it's a fossil and what it is? I'm like,
What?
yeah, sure. And it seemed like a fossil. He thought it might have been from a bison. It was like, it's called a cannon bone. It's basically what would be like the bones in our hand, so like between your fingers and your wrist.
Yeah.
It was sort of the broken off one of those, and I'm like, it looks a little small to be a bison, but it was just like the end of it, so it's like it's basically impossible to tell.
Yeah.
But the first thing I asked him was like, is it heavy? Because that's the main thing. Bone by itself is not all that heavy, because while it is mineralized, our bones are made out of a mineral called hydroxyapatite.
Mm-hmm.
And
Okay.
it's pretty dense. But bone also has lots of less dense stuff in it, like collagen and other proteins and stuff like that, that make it less dense than fossil. Because all that stuff gets replaced with these denser minerals like quartz or calcite. So that's the first thing. If you ever find a bone and you're like, is this a fossil? Is it like heavier than you might think it would be? Then there's a solid chance that it's fossilized to some degree.
Okay.
Exactly how long that takes depends on a lot of things. Depends on the rate of groundwater flow through the soil. Depends what kind of minerals are dissolved in that groundwater. If for whatever reason there is a lot of apatite or hydroxyapatite dissolved in that groundwater, there's nothing to really replace the minerals with. So, if it's the same mineral as what's already in the bone, how does, that kind of makes it a little chemically weird.
Yeah.
And so that's one of the first things. That's sort of like the classic way of something becoming a fossil.
Okay.
And this obviously, this is why one of my favorite lines from an otherwise pretty bad movie, Jurassic Park 3. There's a scene toward the beginning of the movie when sort of Dr. Grant's little sidekick character, Billy, he's like a grad student. They're out on a fossil dig, and he's sort of flirting with some field worker girl. And, she asks, how do I'm having a hard time telling apart the bone and the rock. And Billy just says, well, technically it's all rock. And I'm like, that is the only good part of the science of this movie.
Yeah.
But yeah, because fossils aren't really bones anymore. They're like bone-shaped rocks.
That makes sense.
Yeah.
That's why it's not like just bones that have been buried are a different thing than fossils.
Exactly. And so obviously all of this sort of depends on the environmental conditions of the soils and the sediment that the organism was buried in. So for example, if the soil is pretty acidic, that will over time just dissolve the bones or other, calcium-based hard parts like many invertebrate exoskeletons. On the other hand, plants love getting preserved in acidic conditions. That is their best case scenario. And so partially because those environments are generally bad for animals and many of the bacterial decomposers, so they don't disturb and break up like the very delicate leaves and other structures. That's a big part of it. But just the way plant chemistry works, that's better for preserving them. Whereas animal fossils like more basic, like chemically basic conditions. Just kind of a fun fact.
Cool.
The next one is not quite like a full replacement of the original minerals, but this is called recrystallization. So a little different than the last one. But this is sort of altering the minerals that are present in the organism to become sort of a more stable version of it. And the best example of this is with mollusks. So this is, your bivalves, snails, the various cephalopods that have shells. So this is like as we famously called them, these swirly-shelled squid boys, ammonites.
Big fan.
Big fan. Many mollusks make their shells out of a mineral called aragonite, which is a form of calcium carbonate. However, it's not the only form of calcium carbonate. There's a more stable form called calcite. Even though they are both chemically basically the same, they are both calcium carbonate, their atoms arrange themselves in a slightly different way. And that way, the way that they do it in calcite is more like chemically stable than aragonite.
Okay.
So
what does chemically stable mean?
Basically, think of it kind of like radioactivity, whereas like the way radioactivity works is like, an atom is unstable for one reason or another, and it just will shoot off different parts of itself until it becomes stable. Or rearrange itself in various ways. And that's kind of the way this is, where it's just, it will react less to the chemistry going on around it. And so over time, after a mollusk dies, because it spends energy to maintain the aragonite in its shell as aragonite. And over time, after it dies and stops maintaining it, the aragonite in the shell will just naturally convert and recrystallize to calcite because it is more stable.
Yeah.
That can, it depends exactly on how the bones are, but that can sometimes happen with bones, although it's mostly an invertebrate thing. And then the last one we're going to talk about here at some length is deformation. And so generally, rocks underground are subjected to lots of different stresses. There's lots of pressure pushing on them in all directions. And sometimes that will partially deform the fossils inside of them.
Wow.
And I don't mean like, deformities as we kind of think about with like, things grow in third eyes or extra fingers. Not like that.
Mm-hmm.
But for example, it's quite common for skulls of animals to be kind of like lopsided as fossils. So, leaning one way or another. If you look sort of head on at the skull of basically any T-Rex fossil, you can see that the left and right sides aren't as like perfectly symmetrical as you'd probably expect them to be.
I'm looking right now.
Yeah, so it just looks like it's kind of lopsided, right?
They're all to the side here. I can't get one that's head on.
That's the deformation though. So it's not like that's not the way the fossil was when the animal was alive. It just like slightly warps the fossil so that they are a bit distorted. This is also very commonly seen as like flattened skulls. So not like broken. All the bones are still in the position that they're supposed to be, but they're just sort of like flattened. Either, top to bottom or side to side. That can happen too. And I mentioned skulls specifically because they're the easiest to sort of see this deformation in, but it can happen to any, bone or shell or leaf,
I would need you to kind of point some of these out to me because most of them either just look like wildly decayed and like there's not a whole lot of balance to be had anywhere.
Gotcha.
Or like some of the ones when I look up T-Rex fossil head front,
yeah,
like I could be convinced that one looks more flat than the other, but I wouldn't notice on my own, certainly.
Yeah, I will say if it's mounted up on a skeleton, it's probably
like a good one.
Yeah, it's probably a cast of a good one.
Okay.
So that's almost certainly not the real fossil itself. And that's not a bad thing. There's so many very good reasons to not put, especially like a valuable specimen out on display like that on a mount.
Right.
Yeah.
I will take your word for it.
Okay.
I just don't see it myself here in my Google image search, which, as we all know, is the peak of research.
I tried as well, and I couldn't find any head-on, really.
Okay. Maybe it's because there was, like, one in the museum I worked at in South Dakota that was, like, pretty lopsided. That it wasn't mounted up. It was still, like, in quite a bit of matrix.
Yep.
Anyway, all of these that we've talked about so far are just the things you consider for, like, a single fossil. As always in geology and, most sciences, to be honest, you also need to consider the surrounding context. And so a good example of this is actually the site that I worked on for my master's thesis. So it was deposited about 10 million years ago by a river. And so it was sort of on, like, the slow side of a bend, which is called a channel lag. That's sort of like how there's, bigger pieces, more gravel than sand on sort of the slow side of the river. We call those deposits channel lags. And because of this context, we don't actually know for sure that all of the fossils there are from the exact same time. So, for example, if a bone that had been fossilized previously, so say a T-Rex tooth or something, had, by this point had been a fossil for over 50 million years, if it washed into the river, it very well could have been washed down the river and been redeposited into my site, amongst all the horses and camels and rhinos and stuff.
I see.
That is, a pretty extreme example, but it's definitely like a consideration. And so this is what we call a time-averaged assemblage, because it wasn't like an instantaneous collection. It was an accumulation of stuff over time.
Okay.
And it's also what we call a death assemblage, meaning that all these bones came together after the animals died. On the flip side, we have places like ashfall fossil beds, which we've talked about, several times on the pod. This is an incredible fossil site in northeastern Nebraska from about 11 million years ago, from a time when Yellowstone erupted and spat out likely trillions of tons of ash across North America.
Mm-hmm.
And in this particular spot, it killed and buried a community of animals ranging from horses, rhinos, camels, dogs, birds, turtles, etc. All within a very short amount of time. And so this is what we call a life assemblage, because it is a snapshot of what was living there at the time, captured in the exact place it was living.
Yeah.
Do those two examples kind of make sense and how they're different and how they can sort of give us different stuff?
I think so.
The Mets must be up to bat.
Correct.
Okay, so at this point, we have a fossil or a group of fossils that has died, been buried, and has been changed in some way while underground. Now what? Well, some of these fossils just end up getting destroyed in one way or another. If it's in the ocean, given enough time, the fossils might get subducted underneath a continental plate where they will go deep enough into the earth to melt and form magma, which obviously erases anything remaining of the animal.
There's no... there's no material, there's no minerals that can be deposited. Like, that's just a straight up, you get into magma. Like, yes. There is no more fossil. Okay.
Especially because, at that point, it will be, kilometers and kilometers deep below the Earth's surface. So,
right.
It's just going to melt, and along with all the rocks around it.
Understood.
Yeah.
That is hard to quantify exactly how much that happens.
Yeah, obviously.
Really. Yeah. How would you even,
Yeah.
Find out, because they're gone.
Exactly. sometimes the rocks can get uplifted in a mountain building event, like when, two continents collide. So that's why we get, clam and other bivalve fossils in, like, the Alps. That was a big way that, European scientists figured out that, hey, the Earth changes over time because we have all these ocean critters up at the top of the Alps. But yeah, so over time, that uplift can happen, and when, continents collide, things just get very heated just from the sheer forces of it, and they can get metamorphosed, which also likely erases most of the remains as metamorphic rocks, or sometimes they get uplifted, or an ocean dries up, and the fossils get eroded out and crumble away like any other rock does. So there's lots of ways for fossils to get destroyed before we ever get the chance to find them.
Yeah, that's why they're so rare. Well, one way.
Right. Mm-hmm. And so that uplifting part is really the important part here, because in order for something to get preserved, it often has to be buried pretty deep to avoid all the microbial things that would have broken it down. But if it stays deep, we can't find it. So it has to have been uplifted at some point. Then it is just a matter of chance whether or not it gets found. So, for example, my alma mater, the South Dakota School of Mines and Technology, has at least as of a couple of years ago, has a standing contract with the Army Corps of Engineers to survey different parts of the Missouri River in South Dakota each summer for fossils. And it's a pretty big stretch of river, and sometimes they just can't get to all of it. So if they find something interesting on one bank and spend a bunch of time excavating that fossil, the ones a few banks down that they don't get to might just erode into the river before next year, and then they are lost to time.
Yeah.
So that is just pure random chance which bank they're hopping to that day.
Yeah.
And also, it's the erosion bit is a little bit of a trip to think about in the context of, like, the past as well. Because, for example, we live closer in time to T-Rex than T-Rex did to Stegosaurus. So it is very possible that T-Rex stepped on Stegosaurus fossils as they were eroding out of a riverbank in the area that we call Colorado today.
I imagine there's got to be, like, certain places on the planet that are just more, like, you have a higher hit rate.
We'll talk about that toward the end.
Okay. By the way, the Mets tied the game.
Ooh, nice. All of these things provide lots of room for what we call taphonomic bias. Things that impact the fossil record to make it look a certain way that doesn't necessarily reflect how it looked back in the day. And so the main reason we study taphonomy and why it's important is because if we take the fossil record at face value, because we don't know where these biases are and what effects they have, then we miss out on huge portions of life and Earth's history, and ultimately have an inaccurate picture of what life used to be like on Earth. If we take the fossil record at face value, it is lying to us.
Yeah.
So here's an example. This podcast in general is very vertebrate heavy, much to Fia's chagrin. But when we do occasionally discuss invertebrates, it's always things like bivalves, corals, brachiopods, arthropods, things with hard parts. There are entire phyla. Oh, Mike. There are entire phyla of animals that barely have any hard parts, if at all. Things like ctenophores, which are comb jellies. They're not jellyfish, they're different. Annelids, which are like the segmented worms, like earthworms and leeches. Nematodes, the roundworms. Platyhelminths, the flatworms. And then there are the other, like, a dozen or so phyla of marine worm-like things. Each of those groups has virtually no fossil record outside of some very exceptional sites that are called Lagerstätten.
Yeah.
That are just very unique in their quality of preservation. So, for example, annelid worms, which are, like I said, earthworms, leeches, etc., if you were to take the fossil record of them at face value, you would think that they just show up and disappear for like a few 100 million years at a time, because we just don't have them.
Yeah.
Because you know, most people have like looked at or touched an earthworm. They are completely soft. There is nothing in that to be fossilized.
That is correct.
And you know, that's just animals, let alone groups even larger than phyla, things like the kingdom fungi, in which no members have hard parts basically at all to become fossils. The fossil record of fungi is really interesting because it is better than you might think, but still bad. And here, like I said, if we were to take the fossil record purely at face value, without accounting for the likely dozens to hundreds of soft-bodied species in any given environment, then basically everything we understand about ecology just doesn't work. You know, think about a typical field here in North America. For every, like, single deer that's in that field, how many thousands of earthworms are there?
Yeah.
And that's something that the fossil record just can't catch. So that's something we need to account for in research. And this can also be applied to just like smaller animals, which don't fossilize as well just because they're smaller. Even if they do have hard parts like mice or lizards. This can also be applied to plants, specifically with like their pollen counts. So pollen preserves like excellently as fossils. But the plants that are pollinated by wind produce way more pollen than those pollinated by animals like bees. Mm-hmm. So if you were to take the pollen counts in the fossil record at face value without factoring that in, you might, you know, infer that wind-pollinated plants were way more abundant in their ecosystems than they actually were.
Right.
And it can also make it really hard to tell exactly when a fossil is from. So for example, every now and then, a new story comes up about a dinosaur fossil being found in rocks that are from after the mass extinction at the end of the Cretaceous period. Sometimes, it's just a set of bad dates that, you know, there was some kind of error in their dating method that they just got wrong. But sometimes, it very well could be that the dates that they got were right, and that the dinosaur fossil found in the rocks is from after they should have gone extinct. How can this be? Well, if a dinosaur got fossilized 1 million years before the extinction, then got eroded into a river 1 million years after the extinction, but quickly reburied, it sure would look like this dinosaur was alive when it shouldn't have been.
Yeah.
Obviously, this can make things really, really messy if you just take them at face value. The odds of that happening and it, you know, being preserved long enough for us to see it are astronomical. But it is something that we have to consider because it's something that we could find. And lastly, for the different types of biases here, as we're sort of starting to wrap up, because I know Mike is on a little bit of a time limit.
Just a tad.
Yeah. The last type of bias that we're going to talk about here are the human biases. And so here's just a couple, because there are lots of them. For the first one, for example, my brain is sort of programmed to be looking for bone structures, especially mammalian bones, because, you know, there are subtle shapes and textures that are unique to different types of bones. You know, mammal bones look different than reptile bones, than bird bones, etc. And that's just sort of subconsciously what I am looking for. This, you know, subconscious bias probably makes me a bit worse at looking for invertebrate fossils. Even if, like, I know I'm not going to find any bones in this place. There have been studies examining this. And, you know, while most paleontologists are better than, you know, the average Joe at finding, you know, most types of fossils, people are way better at just finding the type of fossil that they work with more. which intuitively makes kind of sense, right? So if I am out doing field work to help, one of my coworkers collect fish fossils, I am going to miss stuff because that is not my expertise. And that's a form of bias.
Makes sense.
There's also an enormous bias in collection method. Even though it can sometimes involve a crane or occasionally a helicopter, finding and extracting large vertebrate fossils is generally just easier than finding really small vertebrate fossils. Often, finding the really small ones involves collecting a bunch of sediment, washing it through sets of sieves with, in water to catch anything that's in it, and then very painstakingly sorting through all the stuff you catch under a microscope.
Mm-hmm.
Often just to find individual mouse teeth or snake ribs, stuff like that. I spent a lot of time doing this while I was working in the desert in California. And you can get a good flow going with some headphones, and it's not that bad, but it takes forever. And if you breathe wrong, you can just blow that fossil onto the floor, and you'll never see it again. We had 3 to 4 people working on it at a time, and it would take us days to sort through just a 5-gallon bucket of sediment.
Dang.
That would
Really?
often be our entire work week.
Jeez.
So
I don't know. You're not making this profession sound all that appetizing.
It can be really hard. And because of that, and the fact that smaller animals just fossilize less frequently to begin with, small animals are very heavily underrepresented in the fossil record because it is just harder to find them.
Yeah.
And historically, we also haven't really been looking for them that much. It's really fun and exciting to find the big dinosaur. It's less fun and interesting to find the little lizard that was running around between its legs.
Mm-hmm.
But
to some people.
Yeah, but again, you're absolutely right. To some people. But historically, that was the case.
Yeah.
And what, in my opinion, is probably the biggest human-related bias is just where we look for fossils in the first place. So this is coming back to what you said earlier, and I don't remember exactly how you phrased it, Mike.
There's got to be just more hotspots on some place. This can't be just entirely randomly spaced throughout the globe. You would think.
Hypothetically, it should be.
Really?
It depends.
We were talking before about how
it depends
forests...
exactly what you're looking for. So, for example, North America does have more, Cretaceous age rocks than a lot of other places do.
Mm-hmm.
So if you're looking for rocks and fossils from that time, yes, you want to look in North America. But historically, most paleontology has been done in North America, Europe, and to an extent, Asia. That's because those are the places where the largest institutions of learning are globally, and where the most funding comes from. Not just from the institutions, but from the governments themselves. And so it's not like there aren't fossils in the global south, but the local funding to find and study them is often just lower than it is in the global north. And so those, paleo locations and paleo environments are underrepresented just because we have not looked there as much. So, for example, South America, by all accounts, seems to be the best place in the world for a lot of mid-Triassic stuff. So, ballpark 220 million years ago. So, when the first dinosaurs were showing up, that kind of seems like the spot. But, there's a lot of fairly poor countries in South America that just don't have the funding for it because, they need to feed their citizens.
Mm-hmm.
South America's got to get on, is what you're saying.
Well, feeding people is more important than finding fossils.
Yeah.
I'm actually glad to hear you say that, Gavin. Well done.
Thank you. And so, sort of in closing here, how exactly you account for these different biases depends very heavily on the type of research you're doing. So, there is no catch-all way to account for all of these different kinds of biases, just like in any kind of research, all research, regardless of field, even like regardless of like outside of sciences, has some kind of bias in it.
Yeah.
And so
that reminds me, my new scientific paper about.
Oh, okay, yeah. If you send me a link, I will put that in the show notes.
Yeah, sounds good.
But yeah, so the biggest part is saying what the biases in your work are, and then talk about how you address them. So, for an example, I will talk about what I did just a little bit for my master's thesis. So firstly, you just got to be really open about what the biases are. The fossils for my, in the collection I worked with were collected on an active quarry site and were plucked off of a conveyor belt on their way to a rock crusher. Anything small, or like if it was broken so that it wasn't incredibly obviously a bone, was likely missed. That is a form of bias. And that's probably a large reason why most of the bones in that collection are like individual horse toes. Because they're really easy to see and really easy to spot because they have a very unique shape. They didn't really help me with my research much, but that was the majority of what was there. Also, the locality itself, like I mentioned a little bit ago, was a channel lag deposit, meaning inherently this was a time-averaged, assemblage to some degree, meaning you can really only be so confident in your conclusions. Secondly, how I sort of addressed it is I compared my findings like very heavily to other localities that were from less time-averaged deposits that also had better sampling. So like they had better sampling, so they were able to better, say what time their fossils were from, which was the goal of my research. And because of that, because I was comparing it to these other better documented sites, that's the whole point of science, is publicly publishing your data so that it can be used by others like I did. And those other sites were pretty close to mine, which helped me improve the confidence in my results that the site was deposited about 10 million years ago. And with the biases I had, I couldn't really be more precise than about 10 million years ago. And that's just part of accounting for these biases, is your confidence level. And so more accurately to what my thesis actually said, it was sometime during the middle of this land mammal age, which is the way we divide up relatively recent times, called the Clarendonian. The Clarendonian has 3 subdivisions. Mm-hmm. It was during the middle one, and more toward the end of that than the middle, or the beginning. That more or less puts it at about 10 million years. So, about 10 million years.
Nice. Deductive reasoning.
Yeah, well, thank you. And so, that is taphonomy, how it secretly impacts literally everything in paleontology.
Yeah, that seems like a pretty important part of it.
Yeah, and just a little tidbit on how we go about accounting for these biases. Because the fossil record is constantly lying to us, and it is our job to be able to see through that using taphonomy.
Sweet.
And scene.
Mike,
did the Mets do a thing?
Right now, Luis Angel Acuna flared a ball to right field. Oh, he caught it. That's a shame. However, this has been episode 149 of I Wish You Were Dead, the podcast about things that used to be alive. My name is Mike, that was Gavin and Fia, and I will be leading things off next week. But until then, take care, everybody.
This episode of I Wish You Were Dead was written by Gavin Davidson and hosted by Gavin Davidson, Mike Bryson, and Fenella Campanino. It was sound edited and edited for YouTube by Gavin Davidson. Special thanks to former guests of the pod and to listeners like you.